Okay, let's say we have a problem like this, and it's another work kinetic energy theorem problem, but instead of having a block that's being launched onto a horizontal surface at some initial velocity, now we have a block that's sliding down an angled surface, or an incline, or ramp. So here's the problem, and this makes it a little trickier because now there's not just friction acting on the block. That's not the net force. The net force is a combination of friction and this component of the weight. So we have a problem where the block is released from rest atop a 12-degree slope. The height of the incline is 26.6 meters. How fast is the block moving when it reaches the bottom of the incline? Okay then, here's our picture. 12 degrees. When that angle is given, it's always this bottom angle that the slope or the incline makes with horizontal. And that's supposed to say 12 degrees. You can kind of read it. Over here is our block at the very top. Right? And this height of the block, the y leg of the triangle I've drawn, here's a right triangle, this height is 26.6. Okay, so there we are. I've written it in. Now, this is a work kinetic energy theorem problem. So the first thing I'm going to do is write the work kinetic energy theorem. But since we always replace the net work with F net d cos theta, instead of writing W net equals KE final minus KE initial, instead of just writing that, you can skip to the first step, which is to just write that the net force times d times the cosine of the angle between the two is equal to 1/2 m vf squared minus 1/2 m vi squared. And of course, since the block starts from rest, vi is 0, and this whole thing is 0, the whole term at the end, because 0 times anything is 0. Now, to solve this problem, to find the final speed, right, here's the final speed in the equation, we don't have mass, so we better hope that that cancels out. Right? That's immediately what you think when you see that the mass isn't given, because we can't really find it. So what we'll have to find is the net force and the distance and the angle between the two. Okay then, to find the net force, let's draw a free body diagram. Here's my block. We know that there's the normal force pressing up, the weight pulls down, and the friction pulls back. And of course, the weight has an x component and a y component, or sometimes they're called a parallel component and a perpendicular component. And instead of using weight W, I use Fg, because W is now reserved for work. So here's the tilted x component, as I call it, and here's the tilted y component. And of course, this angle is 12. So once we draw the components into our picture, Fgx and Fgy, we could really just erase Fg from the drawing if we wanted. We could just erase it. And we know that Fgy cancels with the normal force. So those forces, they cancel out. We don't have to worry about them when adding the net force. So the only unbalanced force, the remaining unbalanced force, which is the net force, is just going to be Fgx minus kinetic friction. So we plug in Fgx minus kinetic friction for F net. Right? Fgx minus Fk. Now, and let me make sure that that says Fk. Now what we have to do is we have to plug in for the distance d. So this is going to be a little trickier, but not very tricky. There we go, Fgx. If this, well, first thing we have to ask ourselves is, what is the distance physically in our picture? The block is moving down the ramp like this to the end, so that is the distance the block travels. It's the slanted distance is what we have to plug in for d, since d represents the distance traveled by our block. And the block doesn't go straight down, it goes at an angle, which means it travels more than 26.6 meters. It goes a longer distance, d. Since this is a right triangle, and this is the y leg, you could look and see that the sine of 12 is 26 over d, 26.6 over d. So let's write that down. Sine of 12 is 26.6 over d. That means that d is 26.6 over sine 12. So let's calculate that out and then plug in that calculated value right here for d. Okay, what we get when we plug in 26.6 over sine 12 is 127.9. And of course, it's really best not to early round. You don't want to do any early rounding because that alters the answer. Theta, we have to plug in for cos theta here. So we've plugged in for f net d. Theta is not this angle. Don't be confused. Right? That's not theta. Theta here represents the angle between f net and d. So clearly, the block is accelerating down the ramp, which means that fgx is bigger than fk. So if we were to erase this drawing and just draw the net force on the block, here's what it would look like. The net force would pull down because fgx outpulls fk. It outweighs or outpulls fk. So here's what the net force on the block looks like. We have our block, and the net force pulls down the ramp. And that's true for any ramp problem. Of course, the distance traveled is down the ramp, right? So what's the angle between those arrows, those two arrowheads? Well, there's no angular separation. This arrow points down, the f net arrow points down. So theta is 0, and cos theta, cos 0, is 1. So you can just put a 1 here. You don't even have to put a 1. You can just leave it off altogether. But I'm going to put a 1 so that we don't forget what happened to the cos theta. But you do not have to in your paper, or when you're solving this on a test. If you see this on a test, right? Okay, and we have 1/2 mvf squared on the right. We plug in for fgx and fk, and you have to have these equations right at the tips of your fingers, memorized. The x component is mg sine theta, where theta is 12, this theta. Fk is mu mg, of course it's mu k, mu mg cos theta, times 127.9, oops, 127.9, and this equals 1/2 mvf squared. And here's the great thing. Look, earlier we said we hoped that the mass cancels, right? We hoped that the mass canceled because we didn't have any way of calculating it from the problem and it wasn't given. Now we see that there's a mass in every term on the left, here, and a mass on the right. So if we want, we could factor this mass out from these two terms and put an m over here and cancel it with the right side. So m cancels. There's an m in every single term in our equation, so we can cancel it. And so now you have 9.8 times 9.81 times the sine of 12. This theta, remember, is this angle since it came from our tilted block equations, minus mu, let's see, mu wasn't given. Here it is. Mu k is 0.119. Okay, imagine that it was included in the problem. 0.119. And now we have 9.81 again. Cos 12. And I'm running out of room, so I'm going to put d over here on the left. 127.9. And all of that, that whole mess, equals 1/2 vf squared. So you can multiply and add and subtract everything over here, right? Plug that into your calculator. Then multiply the answer by 2 to get rid of the 1/2. So let me show that step. You'll want to multiply the left side by 2, and you'll want to multiply the right side by 2. So times 2 times 2, and that's how you cancel the 1/2 on the right. Then you'll want to take the square root of both sides to get VF squared to get rid of the squared. Square root of that whole thing. And when you do all of this, you get VF equal to 15.156 or 15.2 with sig figs. And that's our answer. So in these problems, you see that all you need to solve is the distance down the ramp, which we could find from the height and the slope angle. You need that, you need the angle for these terms, and then you need mu, which was given over here. It was rewritten into the problem. And with all of that, you can find the final velocity of the block. You don't need its mass at the bottom.